All right, so now we're going to go into some hopefully illuminating cases of these dynamical sections. So it's going to be on gas and stellar dynamics. We're going to start with gas dynamics. And again, keep in mind that a lot of the results are actually quite analogous on the analytical level here, because of this fact that we discussed before the break, that even though the governing parts, the short-range forces that govern gas dynamics versus the long-range gravitational potential that governs stellar dynamics, are very different on that level. Under certain conditions, specifically if you can assume a Boltzmann distribution of velocities, then a lot of the results are analogous, as we will also see. So we have that in our heads also when we develop this section. Now in the gas dynamics parts, we know our equations. We have the conservation of mass equation. We have the conservation of momentum equation. 3 of them, right? There's a divergence there, of course. And I'm going to include here now just a gravitational potential on the right-hand side. And then we have the energy equation and here I'm just gonna, we can have a work terms, but if we forget about those, we can just include here a generic Q dot term to illustrate what will be important for us here. So a few notes here. Now, this is the identity tensor here. So I have already assumed that whatever pressure we're including, it's of diagonal form, right? It's the type of scalar pressure as we discussed during the fall. Now, here is the gravitational potential. So this is then typically governed by Poisson's equation, which is this. Okay? Important for us here, this is just the Laplacian of the gravitational potential, 4 pi g rho. However, here it's actually the total density. And here this can matter because we can have more components than the gas density. This is the governing equation for the gas density, right? But in the gravitational potential, we could, in this context, actually have more components. For example, we could have a gas component, but then, most often the case for us, we will also have a dark matter component that could contribute to this. Now, in principle though, we could also have more. We could, for example, have discrete stars that also add to the density or some other things. And perhaps we could even have a repulsive component here, which we can denote by lambda in this case. Yeah? And that will, of course, come into play when we later discuss the cosmological context. For today, though, we will just keep here, yeah, with the gas component and we will also sort of implicitly have a dark matter component in there. I will discuss that a little bit. Yeah. So that's the gravitational potential. What more terms do we have here? Well, I already mentioned the pressure, right? And the pressure I already wrote as a scalar pressure. And today it will just be the gas pressure, so P gas. Now, in principle, though, we could have other components here. We're very familiar that under certain circumstances we need a radiation pressure, right, as well here. In this course, this comes into play in the early universe, yeah, for example. Now, of course, we could also have a magnetic field in some instances that could enter. And if we want to use simplified equations and we want to account for turbulence, we could actually have also a turbulent pressure here. For example, that plays a very important role in various models in the interstellar medium in this context, right? And you want to set them up and you can't model it from scratch from the turbulence, okay? Now, in the energy equation, we have a generic term here, Q, and that accounts then for sources of heating and cooling. Now, in this particular course, and in the context of galaxy formation, radiative cooling in an optically thin environment plays a very important role. Okay? And then, in this case, we have just denoted this by Q dot. Now, such optically thin, then, radiative cooling is very important in this case to form stars. We know from our other courses that stars form in these molecular clouds, which have cooled down to very low temperature. Yeah? Very low temperatures, so that we can start the gravitational instability and then start to form stars. Okay? Now, in order to have that in a galaxy simulation, you need to get this effect, radiative cooling, decently okay, you know. And we will come back to that in quite some more context when in the later parts of the course when we discuss this. All right. Was there anything more here I wanted to mention in the base equations? No, I think that was it. So then we're gonna start with the first example here, which is hydrostatic equilibrium. Okay? Now, hydrostatic equilibrium, we can see the limit, it's just V equals to 0, and then we look at the momentum equation. V equals to 0 there, and just immediately brings you to this term remains, and we're gonna already now assume that we can set this in a spherically symmetric situation, yeah, such that we have the P gas dr equals minus rho gas, the gravitational potential. Okay? So this gravitational potential, I kept the gradient, but I didn't have to do that because I had already assumed that it is spherical symmetry, right? And in such spherical symmetry, the gravitational potential is just then G, the mass contained up to a certain radius r, divided by r. Where this mass now is then set by the integral up to r, 4 pi, some dummy variable r prime squared, rho of r prime dr prime, okay? Using Newton's theorem. So here we have the set of governing equation then for the hydrostatic situation, let me take away this before we continue to discuss this a little bit. Hopefully this works. Now, again, it's important there that this density now, I didn't write it out explicitly, in the mass, that mass is the one entering through the gravitational potential, right? So this is the total density, or the total mass. So this density here can indeed have these, say, gas plus dark matter, etc. components, such that we identify this with the total mass up to a certain radius r. Okay? The gas, we can say, okay, this is an ideal gas. Then we know this is just rho kT divided by mu mh, okay? Which we can also write as rho a squared, where a here is the isothermal gas speed. Okay, it's a convenient way to write this. It's the isothermal gas speed. Yeah? Mu is just the mean molecular weight as usual, and this is of course then the gas density. All right, so what do we have? Well, we have the rho kT mu mh dr, right, equals to minus rho g, and then we have g m of r divided by r. But here you see that you can solve now using just the hydrostatic equilibrium equation for the total mass of the system. So now I'm going to separate this. I'm going to say that it is the total mass of this system, and you get a r up there, you get a rho down there, so it's just going to be minus r divided by rho g, and then we have d dr of rho g kt mu mh, where we under normal circumstances we can just assume that the mean molecular weight is constant. We can take this out, and then we can just do the algebra here. I'm going to skip a step and write this in a form that you often find it, rkt of r divided by mu mh, and then the ln rho g the ln r plus the ln t the ln r. Okay, so what's the purpose of me writing it like this in this context? Well, what you can see here now, if you have a situation where you can get a system and measurements, say you have measurements of the temperature, right? The temperature distribution from some sort of radiation, and you can do some sort of approximate relation how the gas density should be, right? Then what you see here then is that by actually then adjusting this simple model, fitting the observations for some given temperature, you get an estimate of the total mass, right? Now, this is a very good way of measuring the total mass of, in this case, in the context here, of using the hot gas in between individual galaxies in galaxy clusters. Probably the most important example of this application that we will encounter in this course. Okay? Now, if you do that, you assume that it's in hydrostatic equilibrium. Yeah? You get the temperature from the X-ray emission. You assume some sort of model here. Then you get an estimate of the total mass, because that's governed by the influence. And then again, you can relate that total mass to the amount of luminous mass that you have via this mass to light ratio that we inferred, and see, is there a lot of non-luminous mass in these galaxy clusters or not that we don't see? And spoiler alert, well, the measurements indicate there is. Now, if you think about it, this is actually analogous to what is done in traditional, say, stellar atmosphere work, you know, where you have spectra of a star. You have a model that you assume hydrostatic equilibrium of the star, you adjust it, and then by that you typically derive not the total mass, but we say that we derive the gravity of the object. The gravity, the surface gravity in this case, is just then gm over r squared, which is of course then related to the total mass in view of this. Okay? And that's an analogous, and indeed you can see these type of situations like the gas in the galaxy clusters, they form like a hot halo or an atmosphere in there, from which then you can obtain measurements of the total mass. Analogous as you get an atmosphere around the core of a star. Okay? And indeed it's actually the reason you get these situations are again, you can, in a sense, related to the efficiency of radiative cooling. Yeah? So it turns out that when you do the order of magnitude estimates for the efficiency of such radiative cooling in the conditions of the intra-galactic gas in clusters of galaxies, yeah, then you see that the cooling timescales there are extremely long. That is, that gas does not have time to cool down and form stars. Thus it remains hot, sits there, it becomes essentially in an approximate way in hydrostatic atmosphere. Similarly, if we have conditions where we can cool down, then we cool down, we start to form a star. And this cooling then leads to fragmentation and more accumulation of matter until, well, in this case it's because, typically because we get optically thin, thick, we cannot cool efficiently any longer, and a hydrostatic situation is again formed. Okay? Now, of course, one thing that I didn't mention is this is the hydrostatic equilibrium equation, right? Now, what is in practice often done is that you assume, okay, let's say this is an isothermal situation. In an isothermal situation, you just get rid of this, right? Yeah? Then this is just 0. And then you can see that you can, in this case, go back to your hydrostatic equilibrium equation there, even in this form, yeah? And if you assume, and you put this on the form then of d, dr, O gas, a squared, and that's your isothermal sound speed, you can just put this outside here, right? If you assume that the temperature is constant, and then this is just minus rho g d phi dr, then you see that you have your standard differential equation, the rho divided by rho g, so dl and rho dr equals to the phi dr, right? And that's a type of differential equations we have done in our courses many times. Huh? So this will just come out as then rho equals rho 0 e to the gravitational potential, let's call it then phi divided by a squared, right? Where the gravitational potential here then, if we keep it in that, is just pi divided minus some value at a 0 point, which is where we start the integration, of course. Yeah? This is the thing with gravitational potentials, you always have to start choose a 0 point, you know. Okay, So this is, of course, the standard exponential form of the exponential atmosphere, as it were. Yeah? All right. Now, let's move on with this. Not exactly sure which I should keep and which I'm going to take it away, and then we're going to we'll just put it back, the stuff we need. Yeah. So that was the hydrostatic equilibrium situation with the key application to hot gas in galaxy clusters for our course. Now we're going to take another important example, which is the self-gravitating isothermal sphere. Okay. Lots of words there. Yeah. Again, let's recall the equations. In which form did I want them? Actually, I wanted the ones that I last put down. That is that you had rho g, essentially rho 0, e to the phi divided by a squared, right? Where phi is essentially your gravitational potential minus your gravitational potential of 0, depending on the sign there. And we also had that we took out the a squared, right? It's isothermal. So then we take out the a squared, and then we get the rho g dr divided by rho g, and that's then minus the gravitational potential dr. Okay. Now we're going to put this into the Poisson equation. Okay. Remember, in general terms, we have to solve the Poisson equation, and this is a Laplacian in spherical coordinates, and now we're in spherical symmetry, so we only need the radial, right? That's 1 over r squared then, d dr, r squared, and then we have the phi dr inside there, and that was equal to 4 pi g rho. Okay? Now, for simplicity now, I'm just going to equate the densities because it just, you know, the algebra works out, right? Now, we're going to just call this the total density and say that this is also the total density. Okay? Now, you can carry out the full exercise separating the gas and the dark matter densities, for example. And if they have the same form, you can see then that the solutions also come out with the same form. Okay? Hopefully that's also fairly intuitive to understand. Now, in order to get out the solutions, we're just going to equate this here. Huh? All right, did we want to do something with this, or was it just... Yes, right. So we can see that we can write this in the form of ddr, and then we get a minus sign there, right? But just put the minus sign on the other side. We have the r squared, and then we just replace this by this guy here, but a squared is a constant, right? So we can just write this as dln rho dr, and then on this side we have minus 4 pi g rho divided by a squared. And that's our Poisson equation. Let's see if I did some algebraic mistake there. things should be fine. So, okay. The question is, okay, so this is a differential equation. We can solve it. Yes? I did miss an r squared. Thank you. Very good. I figured I must have done an algebraic mistake because I always do them, right? Thanks. So we have an r squared there. We have density in that. And this is, of course, since a is constant, it's just one single differential equation now for rho as a function of r. And we can solve this. We can solve it numerically, which has to be done if you want appropriate boundary conditions. We will come back to that. But actually, there is a direct solution for it, a mathematical solution, if you will, of rho of r equals a squared divided by 2 pi g r squared. Okay? And I actually will leave you as an exercise to verify this, yeah, by substitution into the equation, which actually is straightforward, just takes you a few lines. You just substitute that solutions, you take the derivative, and you see such that the left-hand side comes out equivalent to the right-hand side. If it didn't, we did some mistakes on the way, but hopefully we didn't. And this is a solution to this differential equation now. That is that this is the density distribution you expect for a self-gravitating isothermal sphere. Now, this is interesting because we can do some interesting stuff with it, right? First, we can calculate now the mass up to a certain radius, right? We had that equation before. 0 to r prime, 4 pi r prime squared, and then we had the density, which we now insert, a squared, divided by 2 pi g r prime squared, and then the r prime squared. And the interesting thing here, of course, is that you see that these cancel, yes? You had a 2 coming out, so it's 2 divided by g, so that's just 2 a squared r divided by g. So you see that the mass of the isothermal sphere increases linearly with r. Okay, now let's say another interesting thing, what type of rotation curves would we get? Let's assume now that we have circular motion. Then we know that the rotation curve, function of r squared divided by r, is just gm of r divided by r. Squared. Because that's the force, centripetal force there. Yeah. So in this case, the rotations, the circular, we can call it, well, we call it rotation curve of r, yeah, is just then g for the isothermal sphere, the singular isothermal sphere, I should say, is g, what is it? We have a square root, yeah? So we have a square root, and then we have g, and there we have m of r. So that's just 2a squared r divided by g, and then we have 1r coming up, and then we have 1r there. So that's just square root of 2 times a. So that's actually interesting, because we said that this was isothermal. And in isothermal situations, a is a constant, because temperature is constant. So it's quite remarkable that this simple self-gravitating isothermal sphere reproduces the flat rotation curve often inferred from ellipticals. No, ellipticals. For spiral galaxies at large distances, as we already discussed to some extent last week, and we will come back to next week. Okay? Take this as a contrast now. What is the rotation curve if you just have a point mass? That is, that the mass does not increase with radius. Then you can see, of course, directly that the rotation curve as a function of r then, just by inserting, will be proportional to 1 over the square root of r. And this is, of course, the Kepler law, right? Because this is how the planets in our planetary system moves, because there all the mass is in the center, right? So the mass is basically constant. All the mass sits in the sun. But that's not the case in the isothermal sphere. We spread it out, and then the rotation curve becomes constant. And here, of course, comes the so to say, the base interpretation of the rotation curves of spiral galaxies. That is that if you think now that you have a spiral galaxy, we remember these, yeah? So I can take them away. If you think now, you have a spiral galaxy here, right? Okay, it has visible mass out to some edge here. Yeah, okay, then you can easily imagine that, yeah, here we have sort of an isothermal sphere, right? As long as we sit inside this. But then you have these neutral gas clouds which live at much further distances out, typically H1 clouds, where you use your 21 centimeter line and the Doppler shift around that, so you get the measurement of these clouds as large distances from the luminous disk, right? And the further you go away, of course, the more and more your rotation curve should approach that all mass sits in the center. So it should approach that of 1 over square root of r. But we sort of never observe this. It's a good reminder, the fact that we seldom observe the decline of the rotation curve. Rather, they just keep on being more or less constant. Now, the constant is consistent with the isothermal model, self-gravitating sphere. And this is the base interpretation why there must sit a lot of material out here affecting the movement of this faraway gas cloud. That's, of course, the non-luminous matter component, which has led to this concept of the dark halos that surround the visible components of galaxies. And we can understand it on a base level from this very simple isothermal model. Now, this solution to the isothermal is called the singular isothermal model. And why is that? Well, it has a basic problem with it. That is that the density, of course, when r goes to 0 in the center, goes to infinity. And that's not a physical solution, of course. The density cannot go to infinity. Yeah? So that's problem number 1. Singular density. Rho goes to infinity as r goes to 0. Now, problem number 2 is, of course, that m of r was proportional to r. So, m of r goes to infinity. That is that there is no cutoff of the galaxy. Right? At some point it has to cut off, right? Yeah. But again, it's a good reminder that we don't really see this cutoff. Very seldom. But it has to. So these two issues one has to handle in this simple singular isothermal model solutions. The first can of course typically can be handled by imposing inner boundary conditions. So you said, okay, but at r goes to 0, so to say, at this very small radius, numerical solution, you say that this is rho 0, and then you say that the rho, or say that when it goes to some r min, which is very close, r min then is much smaller than some scaling radius r Earth. And there you say that d rho, dr, at that position, r min, is 0, okay? And then you get a solution that looks like this instead, where at large distances it will fall off as 1 over r squared, the singular isothermal sphere model, but it will remain finite at your r min radius here. This would be then rho divided by rho 0. So this would be unity, okay? And then you get that type of solution, which of course is a more physical solution, right? The corresponding rotation curve then will increase until it reaches basically a constant value, like this, which also is more consistent, of course. Those are exercises that we will do, by the way. Now, we still have not dealt with this problem of that the mass goes to infinity at high radius, okay? Now, physically, we can understand this in the following way. We assumed that the system remained isothermal, also out to very, very high radii, right? But simply due to adiabatic expansion cooling, we should actually decline. The temperature should decline, right? So we're basically forcing, we have some sort of heating process that we haven't specified, forcing the isothermal condition. So that's physical. What happens is that, you know, at very large temperatures, of course, the temperature drops. And when the temperature drops, the solution here also changes forms because this one is no longer constant. You have to keep it inside here. So when you look at the gravitational potential or equivalent to the density distribution, you get another effect there, and the density starts then to drop steeper, keeping it finite. Now, moving a little bit along to after the next break, when you think about this in terms of stellar dynamics, that's the equivalent of simply saying, okay, let's assume we have a Maxwell-Boltzmann distribution of speeds of the individual stars, right? But of course, that Maxwell-Boltzmann distribution, as we derived for gas during the fall, you know that it has speeds ranging from 0 to infinity, right? But in a real system, if the speed is too high, it won't remain bound anymore. It will simply escape. Specifically, when the speed in the tail of the Maxwell distribution, Maxwell-Boltzmann distribution, is higher than the local escape speed of the system, then of course it will escape, right? So then you have a truncation, a natural truncation there. And then how you model this truncation is not easy, let's just say it like that, but that truncation then can lead to a similar modification as we would do here with the declining temperature, and actually you can think about it equivalently, and then lead to a steeper decline of the density, and thus such that the mass remains finite and not continue to increase linearly with density. This effect is often called evaporation of systems, and it's actually a very real effect, for example, again in globular clusters, where you can have then stars that have too high random speeds, higher than the local escape speed, and therefore are ejected. Yeah. All right. Now let's go to a little bit, and let's use these. Because when we view galaxies, right? Then we can't see the three-dimensional distribution. We see your projected surface density. Compare it to the surface brightness. So if we think about, again, we have some sort of sphere here, right? Oops. Supposed to be round. We have some sort of big R here. We put the longest z-axis here, and we're sitting there, right? And then this would be then the radius of the system, right? Then the projected surface density at some r is just the integral then from minus infinity to infinity along c rho of r dc, okay? And here we can just do it because it's not so. You can see from basic trigonometry here, it is that r squared plus c squared equals to r squared there, such that the r dc then, or r equals to square root of squared plus c squared. So at the r dc then, we get two c's out, right? And then we get 1/2, and this comes in the denominator, square root 1 rc squared. So this would then be just that's a 2, that's not a c. It's like c divided by r, okay? So if we just use this substitution, then we take into effect the symmetry, then we can see that the surface density is just 2 times 10 from a minimum c min equals to r to infinity, and then the density, and then we just do the substitution here such that we get an r there, we get a dr there, and then we have a c in the denominator, which would then just translate to square root of r squared minus r squared. Okay, so here we have the projected surface density expression. Now the question is, of course, in general, for a given density distribution of your given model, you would have to solve this numerically, right? But for the particular case that we were just discussing, that is the singular isothermal sphere, you get an analytic result, which again I thought you can verify for yourself. Which I leave you as an exercise to find out, okay? For the singular isothermal sphere, then you can solve this analytically. I actually realized that I wanted to take another example, and that is that when you modify your isothermal sphere to take into account the physical inner boundary condition, that is the curve that goes like that, and you look at your numerical solution, then you can find that a good analytic approximation for radii below and approximately at some r0, which we will come back to, is rho of r is approximately rho 0, so the value here, right? Rho divided by rho 0, so that will be 1, and this would be then r divided by r0. So rho 0, 1 plus, I have to look this up, sorry for that, 3 1/2, and then to the power is the other way around. Oh, it's early in the morning also for me. Like that, okay? And under those conditions, the projected surface brightness here can be solved analytically to yield I'm going to look it up, non-zero, 1 plus R divided by R0, 2 minus 1, where epsilon 0 is 2 times rho 0 R0. So that's the surface density that's the core surface density. Okay? So what you can see now is that the fall off, it became a little bit messy on the Blackboard now, so I'm going to actually take away this so that I don't confuse too much here. It's a bit inconvenient not having more. Then you can see that if you now insert the projected surface density, the projected radius of R0, and then you divide that by the core value, that's just 1/2, right? Because this would just be 1, so this is just 1/2, okay? Hopefully very straightforward to realize. So this radius now is therefore often called the half-light radius, which is, well, perhaps not the best terminology because it's really the radius at which the projected surface density goes to half, okay? And this is the analytical approximation. You get a small numerical difference if you actually were to integrate this now and then use the projected surface density. But that difference is actually, the analytical approximation here is good for this part. The radius R0, you might wonder about, and that comes out from the scaling analysis. Let's see if we remember the formula. It was something like this, right? dl and rho dr, and then we had 4 pi g rho divided by a squared. So if you now scale all your densities to some sort of density divided by a surface value, and you scale all your radii to some R0, then you can just use dimensional analysis here and then a suitable approximation for R0 squared in this case, because it's a square there, would be A divided by square root of 4 pi g rho. And then typically here we have a 3, which is inserted, so you end up with a 9 here, because then these dimensions then and the half-light radius come out in this particular way. This is called the King radius. After the King models that I will discuss toward the end of the class, which are essentially the isothermal models here, but where you're using an approximation to take into account this effect at the outer radii that we were qualitatively discussing. That is that you're going to have to truncate the Maxwell distribution at some point to account for this fact that above a certain threshold, you know, stars will start to escape. Yeah, and that's a certain class of models that uses an approximation to truncate that, and whereby you can then get a very similar numerical solution to this equation, and you derive something which is very similar to this analytic approximation for the one which takes into account the finite lower boundary condition in this part. But instead of just decreasing with 1 over r squared, such that the mass remains infinite at higher radii, it actually lowers that such that you remain finite. Okay? And that's that class of models, and this is the typical scaling radius then that comes out from those, called the King radius. Now, of course, the interpretation here of the projected surface density is in terms of relating it to the observations of surface brightness of real galaxies that we introduced last week. And these type of models are indeed often the ones that are used to compare the observations of such surface brightness profiles. All right, let's take a short break again.